Welcome to Pomodoro Joe for Tuesday, September 26, 2023. Today we're looking at LeetCode problem 316. Remove duplicate letters. This is a medium problem. Given a string S, remove the duplicate letters so that every letter appears once and only once. You must make sure your result is the smallest in lexicographical order among all possible results. So this is just saying it has to be the smallest in alphabetical order. All right, so we have an example, BCABC, and we remove BC, and we just end up with ABC. All right, so this is actually a pretty tricky problem. Now, I wish I had a way to explain this from first principles. Unfortunately, I don't. This is one of those problems that you at least I did, I just have to kind of memorize this one. So one thing, I guess, one way to start from basic principles is we're going through a long string. Order does matter, so we can't just throw everything into a set. We have to maintain the order. So we have to have some kind of ordered data structure for this. We know that our future might affect the past. So if we choose a letter now, so if we go B, well, we haven't seen B yet. Then we go to C, and we haven't seen C yet, so we might want to keep B and C. Then we go to A. Again, we haven't seen it yet, so we're kind of keeping either a queue or a stack. We're keeping track of the things that we've seen. Then we go to another B. Now we have to check, have we seen this B already? Which B should we keep? Do we keep this new B or do we keep the old B? This is where we have to make a decision, and it's kind of based on both the past and the future. What if there's another B in the future? Or in this case, let's say, oh, well, we don't want to keep this first B, so we'll take the second B. Well, I guess the question is, how do we choose which B do we keep? Well, we could look at BCA. That's what our string is so far. Or if we drop this B, we'd have CAB. All right, well, CAB is actually lexicographically later on than BCA. So we might say, oh, well, we'll keep the first B because that actually gives us the better answer. However, when we get to this next C, then we say, oh, well, if we look at these two C's, which gives us the better answer? We had BCA, or we'd have BAC. Well, we might choose BAC as our answer because that's smaller than BCA. So we go BAC. Yay, there's our answer. But that's not the right answer. We want ABC. So choosing which B is actually dependent on which C we end up choosing. So we have to keep track of not just the past, but we have to know the future. Oh man, so how do we do this? Well, we'll put 25 minutes on the Pomodoro timer and we'll get started. So this one, again, like I said, I kind of just have to memorize this one. So this one we will be using both a stack and some forward-looking, some future-looking data structure. So in our case, I guess I'm just going to use the string to start with as our future-looking data structure. So we'll have a stack. So we'll start with some stack. Now we're going to go through our string one character at a time. Now if we have a character that's already in our stack, that means we're happy with what we found. We're just going to leave that character in the stack. No changes to the stack. Now if we find a character that's not yet in the stack, well, in that case, we'll need to check, should we put this character in the stack, or is there some future character or some future index of this character that's actually going to be better for us? Again, I wish I had a better way to explain this, but unfortunately I don't. So here's the basic outline. So go for every character in our string. If this character is in our stack, we've already seen this character, we've put it in our stack, we're happy with it. We'll just continue. If the character is not in our stack, that means that this is a new character to us. Now at this point we have to decide, do we keep this character? Do we put it onto our stack? Or do we drop it? Well, we're going to keep this character because we don't have it yet, so this is the best option we have so far for this character. But the question is, do we keep the other characters in our stack? And that depends on where this character fits in. So if this character is actually less than the other characters already in our stack, so lexicographically less than. So if this character is lower in our lexicographical order than our characters in our stack already, we might want to replace those characters, but only if we know that there's a future character of the same value that's coming up in our string. I know this is super weird. So, at least it's weird to me. So for this case, we basically want to check. So while we still have some stack, and while our character, this character that we're just about to pull out of the string, while this is less than the top of our stack, so the character at the top of our stack, that's stack -1, we're going to pop that character out of the stack, but only if we know there's another one of those characters in the future. Because if we pop this out of our stack now and we don't have another one coming up, then we've just lost that character and we don't have our complete answer. So while we have a stack and this character is less than the stack or the top of the stack, and this character, or sorry, not this character, the character at the top of the stack, so stack at -1 is somewhere in our future. And in that case, I'm going to use, well, let's see, I'll just call it future here. Now, I haven't defined this yet. We'll come back and replace that later. So if we still have some characters in the stack, and this character happens to be less than the top of the stack, and we know that character at the top of the stack is going to be repeated sometime in the future, well, then we'll just pop this character out of the stack and we'll push our new character onto the stack. So our stack will pop at the top, which is -1. And then once we've popped all the characters that we know we're going to have future versions of, then we can put this new character on the top of the stack. So our stack dot append this character. All right, now this future, I haven't defined this. So I'm going to do this the dumbest way possible right now. And that's just to look forward in our string from this index into the future. So I need to know the index of our current character. And one way to do that is just to enumerate our string as we go through. So we'll have this current index and our character in the enumerate of string. And that means this future is just this string at this current index +1 to the end. Again, so we're going to take the string, we're going to start at our current index +1, so that's the index of this character, and then we're going to go to the end. That's what this little colon means. All right, now we'll go through, we'll be replacing characters or popping characters off our stack if we know we have a future one coming up and we know that this character happens to have a lower value. Then we'll basically end up with a stack that just has all of our characters that we need for our result in the proper order. Because we popped all the future ones off, we've basically percolated all of these lower valued ones toward the front of the stack or the bottom of the stack. Now to convert our stack into a string, we use the join operator. So we will return an empty string dot join. And what this will do, it will take, basically it'll iterate through all the characters in whatever we pass into it, all the elements of whatever we pass in, and it will append them to this string. And that's going to be our stack. So we empty string dot join our stack. All right, let's give it a shot, see how we do. Again, this is not the cleanest, but I wish I had a better way to explain how to get to this answer other than you just kind of have to memorize it. All right, let's run it. Okay, so this works. Let's submit that and see how we do. And we pass. And we actually do better than I thought. We beat 79% for runtime and 52% for memory. Yeah, so that's not bad at all. Especially considering we're just like searching through a string. That's surprising me. All right, and why does this work? Well, basically we are building up our result by knowing the future. That's what this is doing here. We're looking ahead to the future to say, I know that I have this other character, this character is going to come up again in the future, and I have a new character that I haven't seen before that has a better place in my result than the current characters already in my result. So I'll just take those characters out of my result because I know I'll find a better place for them in the future, and I'll put this character in its place. So How can we boost the speed on this? There's kind of a few things we can do. I already mentioned that this is probably not the most efficient. We're essentially just going through this string character by character over and over and over again, looking for the character at the top of the stack. So what could we do to make this a little bit faster? Well, one thing we could try is let's just keep track of, well, what is the last index of every character? So we'll have a last index of character, and that's just going to be a dictionary. So we're going to go through S again, I and C in enumerate. All right, so we're going to go through S, and we're going to keep track of the last index that we see each character. So the last index of this C is just equal to this index. We'll just be replacing our indices as we find a later index for this character. All right, so we build up this dictionary that gives us a mapping of our character to its last index. So then instead of searching for this entire thing, like searching the string entirely again for this new character or this character at the top of the stack, we can just check the index. Is this character's index greater than our current index? So let's get the last index of this character. So the last index of the character that is at the top of our stack. And if that is greater than, I guess you could say greater than or equal to, but it shouldn't be the same character. Greater than, well, we'll do or equal to, why not? If that's greater than or equal to this current index, well, then we know that we have a future version of this character coming up, and we can replace it. All right, let's see if this still works, and then we'll see if it helps. Okay, it still seems to work. Let's see if this helps us any. Looks like it actually hurts us quite a bit. So we went from a 79% runtime down to a 48% runtime. That's surprising, considering we have to search the string over and over and over again, whereas this case, we only had to go through the string once to keep track of these values. That is shocking. All right, another thing we can do, kind of the same thing. Every time we go through here, we're looking for our C in the stack. Now, instead of looking for the C, like iterating through our stack, looking for this character, we could just keep track of which characters we've seen. We could have a set. So this we can do, we can have a scene set or a result set. Maybe I'll do that. I'll do scene, why not? No, I don't want to do scene. I'll call it result, only because, sorry, I should explain this. We're going to go through, instead of looking for C in the stack, we'll be looking for it in our set. Maybe I'll call it the stack set. There we go. Stack set, and that's just a set. So instead of searching for C in our stack, we'll just see, is it in the stack set? And if it's in the stack set, we'll just continue. Otherwise, when we get down here, we'll be putting our character into the stack set. We'll add character C. So when we put our character in the stack, we're also going to put it in the stack set. But that does mean that when we pop it out of the stack, we're going to have to pop this character or remove this character from the stack set. Let's remove removed character. And this removed character I'm going to get from popping it off the stack. All right, so now we're using a set, which is an O of 1 operation, to check to see if we have already seen this character instead of, or if this character is in our stack, rather than searching the entire stack every time. Still works. Let's see if that saves us anything. And that does, actually. So now we're up to an 89% for runtime and a 52% for memory. So hey, that's not bad. I wonder if going back to our string thing would make it better. I don't know, I'm skeptical that this was really a worse solution, but let's see. Let's go back here. Try this again. There we go. Whoa! And now we're up to a 92% for runtime and a 97% for memory. That's crazy. So searching the string again is actually faster than if we just had indices? That makes no sense to me. All right, maybe you know how that works. I don't know how that works. That shouldn't happen. If you know why that's happening, please comment, explain it to me, because that makes no sense. All right, Well, sorry about this one. Unfortunately, this is just one of those that I don't know, you learn it, you just kind of have to memorize it, practice it. I don't know a good way to derive this on the fly if you had to. Well, that's it for me. I hope you enjoyed this. Hope you had fun. Hope you learned something. Hope you can go out and write better code.